B says y equals 5 minus x to the 1/3 power. And remember, guys, we are still looking for all of those characteristics as in A. It wants us to find the increasing interval. And remember, increasing interval is when the first derivative is bigger than 0. Then B, it wants us to state the decreasing interval is when the first derivative is less than 0. C, it wants us to find concavity. So concave up, that's when the double derivative, guy, is bigger than 0. Then concave down is going to be second derivative less than 0. And it wants us to find the extreme values. So that's going to be letter E. We want to find the local min. Now remember, the local min is when the first derivative goes from negative to positive, okay? And then we want to find the local max is when the first derivative goes from positive to negative. And then we want to find the inflection point, so IP. Now, inflection point is the second derivative test, is when second derivative is positive on one side and negative on the other, and vice versa. So, all right, so let's go. As you can see, we will be using first and second derivative, so let's just find it all, okay? So first derivative, let's go and do y prime. Y prime is going to be 5 is a constant, so the derivative of that is 0. We will drop the power down for the variable x and subtract 1, so that will give us negative 2/3. It would be easier for us to solve for the critical points, so I'm going to rewrite it as a radical, okay? So the critical points, guys, is when the derivative is 0 or when it is not defined. So right now I'm going to set it equal to 0. As you can see here, it is not possible to solve for x, okay? There's no x value that will give the y prime equals to 0. So we can't really do that. But as you can see, we can go and see when it is not defined for the first derivative. Well, because we have an x that's in the denominator, so that means x can never ever be 0. So this is the critical point since y of 0 is okay to have, because y of 0 is just 5 minus 0 to 1/3, which will give us 5, okay? So that's why this is a critical point with a y value of 5. Now let's go and do our second derivative as well. So second derivative, I'm using this right here. So it's going to be negative 1/3 is a constant. Drop down your negative 2/3 as a power. Then we're going to subtract 1. So that's going to be negative 5/3. Very similar to what we just did with the first derivative. We're going to make it pretty. So it's going to be a positive 1/9, and it's going to be a cube root of 3 with an x variable to the 5th power. As you can see, we can't really solve for x if we set it equal to 0. So there's only one value that x cannot be. X can never ever be 0 again because it's in the denominator. Okay, so here we have all three equations. The first original equation, f of x, or y equals 5 minus x to the 1/3. We have the first derivative, we have the second derivative. Now let's make the number line for the first derivative and the second derivative. Okay, so we only have one x value. Oops, we only have one x value to use, guys. So it's going to be x value. This is the first derivative, and then I'm going to make another number line for the second derivative right below. Oops, right below it. This pen is way too fat. Right below it. So, and then again, x value should be exactly the same for first derivative, second derivative, or the original. And what we want to do is we want to plug in f prime of a negative 100, and then f prime of a positive 100 or 1,000, just to see the behavior, okay? This is what I'm going to use for f prime. When we plug in negative 100, everything is square in the denominator, and we have a negative 1 on the top. So that means it's a negative on top divided by positive on the bottom. So this is going to be a negative. And similarly, when we plug in a positive 1,000, a positive 100 on the for the right side, we're going to say, okay, well, on the top it's always negative 1, so that's always negative. On the bottom, again, everything is square, so everything will be positive on the bottom, so that again is negative. And we're going to do the same thing on the second derivative. Okay, we're going to say, okay, let's try to plug in something negative big on the left side, something positive big on the right side to see the end behavior, and I'm going to use this right here. So on the top, we know it's always positive 1. Now on the bottom, because it is an odd power and it's a cube root, so it's a negative, it's a positive on top always. On the bottom, if we plug in a negative 100, negative 1,000, the denominator will be negative, so this will come out to be negative. Now when we plug in a large big value such as 100 or 1,000, on the top is always positive 1. On the bottom, a positive number to the 5th power and then take the cube root is always positive. So on the right side, it's always positive. That will help us figure out all of the answers here, guys. Okay. All right. Increase is when the first derivative is positive. So as you look at this, the derivative is never positive, so this would never be an increasing function. So the entire way, guys, is always a decreasing function, and it's probably because of the cube root, okay? So if you think of a cube root and it's negative, so it's a reflection over the x-axis. So a positive cube root, the parent function, if you remember, it looks like this, like that, right? It's always positive, but because it's a reflection and it's shifting up 5, so it's going to be like this. So it's always negative. Decreasing. So decreasing from negative infinity all the way to infinity. Now we include all the way to infinity is because even though 0 for the first derivative was not happening, but the value of the original does exist. So because the original is 5 minus x to the 1/5, right? It's decreased the entire way. The concave up is when the second derivative, guy, is positive. So it's going to be on the right side. So that's going to be from 0 all the way to infinity. Concave down, if you look at the second derivative, is on the left side. So that's going to be from negative infinity to 0. Now we want to look at the first derivative for the local min and local max. Well, local min and local max is when there's a change in first derivative. And if we look at a first derivative line here, there is no change. It's not a positive to increase, a negative, or vice versa. So there's no local min and local max, okay? So we're going to write none for both. And then last one, it says, hey, second derivative will give us the inflection if there is a change from positive to negatives or vice versa. And we do have a change. We have a change from a negative second derivative to a positive second derivative. So we have an inflection point, even though, again, it does not, the second derivative and first derivative, x does not exist at 0, but because it does exist in the original, we still have an inflection point, and an inflection point is at 0. Plug into the original, okay, and we plug into the original and get 0,5 because we did it right here, okay, and that's the end of example 4b.